Good morning, everyone. I am Pinki, Dr. Pinki Malik, ANRF and PDF holder at IIT Mandi. Right now, I am working with the Dr. Ranbir Singh, and my research area is focused on the uh, low dimension perovskite material for optoelectronics applications. So today, it's my pleasure to share my research finding with all of you. So, firstly, I would like to introduce about the perovskite materials. Why the perovskite materials have attracted enormous attention in past few years, as perovskite material have some outstanding property like the strong light absorption, tunable band gap, high carrier mobility, and importantly, they have the low cost solution processability. And the formula for the 3D perovskite material is ABX3, where A is the monovalent cation, B is the metal divalent cation, and X is the halides. So, due to their outstanding optoelectronics properties, they have the wide range of the application in photodetector, solar cell, LEDs, medical imaging, machine vision, visible light communication, etc. So these, as I discussed, these 3D perovskite material have the excellent property like the high power conversion efficiency, tunable band gap, strong light absorption. So there are some key challenges associated with the 3D materials, like they are the moisture sensitive, thermal degradation, and the trap state and the grain boundary. So to overcome all these limitations in the 3D materials, researcher has introduced 2D organic cations into the 3D materials to make the moisture resistance and more thermal stables, and to decrease the dark current, and for reduce ion migrations, because 2D cation are the hydrophobic into the nature. So after covering onto the surface of the perovskite materials, these reduce the penetration of the moisture into the perovskite film and increase the environmental stability of the devices. So till now, in my application, in my research work, I have employed these 2D perovskite material for the application of the photodetector. Photodetector is a device which convert the light into the electrical signals, and it has the application, as I have discussed, into the medical imaging, optical communication, imaging, machine vision, etc. And in market till now, photodetector coming into the markets, these are the based on the silicon and the gallium nitride, but they have some limitation like low absorption, complicated manufacturing, like sputtering, photolithography, and need free amplify for weak light detection, and low quantum efficiency, expensive fabrications. So all these limitations, all of these limitations motivate the researcher to search for the new materials which has the low fabrication cost, low operating voltage, high the flexibility. So the 2D perovskite materials contain all these properties. So in my work, I have employed these 2D cation perovskite for the fabrication of the perovskite materials. Initially, I have fabricated the salt, and then after the synthesis of the 2D salt, I prepared the solution by equally mixture with PbI2 in DMF, and prepare the homogeneous precursor 2D solutions. And then after that, this solution is been coated onto the desired substrate, followed by the annealing at 100 degrees Celsius for 10 minutes, result into the formation of the 2D perovskite thin film. Then we have characterized this thin film for the structural optoelectronics properties, and from the XRD spectra of the thin film, it can be seen that there are some sharp diffraction peaks which indicate the higher crystallinity of the devices. And these diffraction peak are associated with some assigned higher oriented planes, and these higher oriented planes indicate the higher efficiency of the devices. And from the contact angle of the thin film, it can be seen that is near about 131 degree, which is the super hydrophobic and increase the environmental stability of the devices. And from the UV visible spectra, it shows the absorption as, and near about 520 to 520 nanometer wavelengths, and so it indicates the highly pure phase of the 2D materials. And from the tau plot, we have calculated the band gap, which is near about 2.31 electron volt, and the narrow peak into the photoluminescence indicate the higher crystallinity of the devices, which is good for the higher performance of the optoelectronic devices, and it shows the strong green light emission under 520 nanometers. So as prepared material is a wide bandgap semiconductor with efficient green light suitable for the optoelectronic applications. Finally, we have prepared the photo detector device, and which has the gap between the electrode is 30 micrometers, and this gap contains the active perovskite materials. Then we have measured the IV characteristic of these devices under the green light emissions, and it has been found as the intensity of the green light goes on increasing, there is the increment into the current, and then finally calculated the quantum efficiency, responsivity, and the detectivity of the devices. So it has been observed that with increase into the intensity, all these parameter goes on decreasing, because with increasing into the intensity, there is increment into the strong hole pair electron hole recombination. And we found that responsibility and the detectivity of the device is similar or much superior than the 3D perovskite material. In addition, they show the higher environmental stability compared to the 3D materials. Further, uh, I want to conclude my work. Uh, um, I want to conclude my work that by introducing the future perspective of the 2D materials. So finally, we want to make the solar device fabrication where 2D material is used for the passivation of the defect, and when this 2D material is spin coated onto the 3D perovskite surface, so it passivates the defect and increase the hydrophobicity of the devices, and increase the stability of the devices in turns. And finally, and another research direction is that we want is to make the cell powered devices, optoelectronic devices, uh, which eliminate the requirement of the powers, and it has the many application like integrated recognition, lip motion, pulse monitoring, and the wound healing, etc. And finally, I want to acknowledge my supervisors, my sincere gratitude to my supervisor, Dr. Ranbir Singh, then ACL lab members, and IIT Mandi for providing me the facility to continue my research. And finally, I want to acknowledge ANRF for providing me the fellowship to continue my research work. And thank you, all of you, for your attention.